Hello, and welcome to the CPM webinar series. Today's topic is machine-to-machine transfer of applications. My name is Christian Davis, and I'll be your moderator for today's event. With locations around the world, CPM is a leading global supplier of twin screw extruders, extrusion systems, high-performance replacement parts, ring extruders, thermal equipment, and supporting services. Our webinars are intended to service, support, and inform you about the latest technologies, maintenance methods, and trends in the industry. Presenting today's webinar is Daron Fraim. Daron has over 20 years of manufacturing experience in various industries, including thermoplastics. More than a decade of his work has been directly related to extrusion compounding using co-rotating twin screw extrusion technology. At CPM, Daron works closely with our customers to support their application needs with respect to machine configuration, screw configuration, technical training, and other process improvement initiatives. If you have any questions during the webinar, please type them in the questions field. If it's not answered, you'll receive a follow-up response by email. Daron, I'll now turn it over to you.
All right, thanks, Christian. Welcome everyone to this month's webinar on machine-to-machine transfer of applications. And I will start with just noting here that this webinar will, one thing to say about this is we're going to focus on specific energy input is kind of the main key point here. Anytime you're moving applications, whether from a lab line or from production machine to a larger or smaller, vice versa, the idea here is to transfer with similar energy input on both machines. And so this webinar is going to really kind of dive through and look at some differences in these machines. Now some of you may have newer technology or control systems, HMIs on your equipment that may display specific energy real time. And so, or you may have the capability to see that. So it makes life a little easier, but this webinar will kind of walk through and say, okay, even if you don't or do have that capability, we'll look at some things you can do ahead of time, so to speak, kind of doing your homework to say when I'm moving from one machine to the other, what are some things I want to look at and some differences on these machines. And then some calculations. It will get a little math heavy during the webinar, but I'll explain as we go through. But you can see here on the outline that, the first thing to do is to scale comparable screw configurations. And then again, as I've noted, specific energy input is the key variable for most applications. If you can move from machine to machine and mirror that specific energy input, you should get very, very similar properties. We'll look at comparing similarities and differences of the two machines. We'll talk about volumetric scale up or scale down. We'll look at power requirements. We'll look at degree of fill. And we'll look at diameter to clearance ratio and wear conditions. We'll talk about that as well. And then again, this will be kind of centered around pre-evaluation prior to application transfer. So when we talk about the screw configuration itself, the idea here is to match as closely as you can similar geometry. So you want to look at these elements, both conveying and then your mixing elements, and try to match those. And we'll look at the L over D relationship on the two machines. For example, this here is a 26 millimeter lab machine. And so you want to try to use the same type of kneading blocks, number of lobes, stagger angle, pitch, and length. When we talk about pitches on your conveying elements. So here is we're going to look at conveying elements as the first step here. And so the idea here on the conveying elements is you want to match the same pitch. And so what that does is from machine to machine, you're trying to match the channel volume in efforts to kind of maintain the same degree of fill under the similar conditions. So for example, if you see here, this is a 26 This first element is an SE. It's a standard conveying 4848. The first number is the pitch. And so when I look at this element and I say it's a 48 millimeter pitch and this is a 26 millimeter diameter machine, that means that pitch is 1.85 times my diameter. Same thing on 2424. If I look at that and break it down, it's a 0.92 L over D, or 0.92 times the diameter. And you can see the same for the 18 millimeter pitch, 26 diameter. So I'm looking at my pitch relative to my diameter size, and I'm looking at that ratio. If you look at the kneading blocks, I'm going to focus on the length. Again, you want to keep the same stagger for each type of element. So for example, the 12 length is 0.46 of the diameter. And you can see as you proceed 24 length, 36 length, and so forth. So when I translate to my 70, I want to kind of try my best to match that equivalence in L over D. So for the 4848 element on the 26 machine would equate to about a 130 for the 70. Because if you do the math, 130 pitch divided by 70, you're going to be pretty close to 1.85. And you continue the same strategy here. Same thing on the kneading blocks. If I look at a 0.46D, for example, that first one on that 26 machine is 12 millimeter length. I want to be about a 32. Now you may look at these geometries on the right for a 70 and say, well, I don't have that exact dimension. So you want to get as close to that as you can. And as you can see here, when I start matching these machines, not only do I want to kind of each individual element type to try to be as close as I can in terms of its pitch on the conveying, relative pitch length relative to diameter of the machine, but also the overall length of the conveying sections. As you can see here, I'm 9.9 L over D on the top one, 9.5 L over D. That's total conveying length. Same thing in the middle here at 7.8 on the small machine, 7.9 on the larger, and so forth. And if you look on the left here, I've noted the 4848 is a 1.85D for the small machine. I went with a 13567.5, which comes out to about 1.9D on the 70. And then on the small one, the 1818, I'm about 0.7D. We're on the 70. I used a 4545, so I'm 0.64D. So the whole idea here is to try to equate these geometries relative to diameter size. Next here is to kind of look at the kneading block sections. I'm doing the exact same strategy. When you look over here on the far left, I'm looking at the different size kneading blocks I have on these configurations. I have 24 length, 36 length, and 12 length. And you can see I'm 0.9D, 1.38D, 0.46. If I look at the 70, I went with a 60, which is 0.86D, relatively close to 0.9. I went to, the 90 was 1.29D, and then the small 30 was 0.42D. And then the same strategy in terms of total mixing length. When you look at each section, on the top one, I'm 5.5 total L over D length to diameter ratio of that machine. And then I'm 5.1. And so the gist here again is just to try to look at each individual element type, match the pitch on conveying as closely as you can relative diameter, and then total conveying length. Same thing on kneading, the kneading block length relative to diameter of machine, and then total length of the mix or the kneading block sections to try to match those. Now, one thing on the previous slide, you'll see these two machines are both 10 barrel 40 L over D machines. So it makes life much easier when you're really matching screw to screw, because you have the same process length in terms of length to diameter ratio. And here, so what we'll look at here is when we're talking about, okay, well, now what if we're dealing with moving from a 40 10 barrel 40 L over D to a 48 and vice versa. And you can see the strategy here is the emphasis is to try to match the melting and mixing length and make the adjustment on the solids conveying. So for example, if I move from a lab machine that's only 10 barrels and I move to a production machine that's 12 barrels, then I'm going to have a little more solids conveying length on that longer machine because my focus is the melting and mixing areas is where I want to keep equivalent, because that's where the primarily majority of the energy input into the material takes place. Same thing, strategy on the going the opposite direction. If I'm moving from a 12 barrel to a 10 barrel, then I'm going to have to reduce my solids conveying. Now, there will be some limitations how much you can. You've got to have some conveyance length. So as best as possible to try to mirror and match more of the melting and mixing section. And here, this will kind of break down why that is the case. Because when we look at total energy going into the material, we want to see where's the majority of that happening. And this is why you want to start or try to match and mirror the beginning point of your kneading block section, which in the case here is your melting section, that first kneading section on that machine. And then now everything's in melt phase past that. So your second, third, and fourth sections of your kneading blocks is your mixing, incorporating additives and dispersion and distribution. So you can see here, if I look at my total energy, I've got 45.3 kilowatts of melting, 14.8 kilowatts of viscous conveyance. That is the energy it takes once you've melted the material. It's going to take nearly 15 kilowatts just to convey it through the machine. And that's what we call viscous dissipation or viscous conveyance. And this is a simulation I ran. And if you look here, I've got 6.2 kilowatts of electrical heating input. So when we're looking at electrical, thermal input from electrical side of things. So my total energy package here is 66.3 kilowatts. But if you look starting at that first section, it took 45.3 kilowatts to melt, 14.8. That's 60 kilowatts, just a hair over 60.1. So 90% of the energy input is taking place once you move into the melting and going forward downstream in the process section. So that's why it's key here to when you're moving from machine to machine with different L over D length is the solids conveying very minimal energy input. There's a little bit of electrical going in to begin to start heating the polymer or powders going in. But 90% of your energy is taking place once you get into the melting and then moving forward. So that's why it's key to focus on that location. So the whole idea of the webinar is to try to match your specific energy input. So for example, the specific energy is a measure of how much mechanical work input is imparted into the material. And that's the key thing here is when I move from machine to machine, I want to make sure I try to mirror that specific energy input. So we'll look at the two machines and we'll take a look here and we'll compare some things and what's similar, what's different. You can do your homework ahead of time and kind of understand some key differences and things you just want to be aware of. One thing to note, when you move from small machines to larger machines, the one thing that's changing is the free volume changes at a higher rate than your surface area. And so oftentimes we say the surface area is changing on a squared term and the free volume on a cube term. So to the power 3 versus power 2. So that free volume is growing at a faster rate in your surface area. So what happens is, as you move across different machine sizes. Now, machines growing in size, it's getting less and less efficient at thermal transfer from electrical conductive heat transfer. And so you can see here's an example. If I look at a 45 millimeter machine and I move to a 70, that 70 is going to have about 1/3 the efficiency of heat transfer of that 45 machine. And this gets more critical when you're dealing with thermally sensitive, or you need to really take a lot of heat off the process. Maybe you have a reactive extrusion that's exothermic, generating heat, and you're really requiring to try to remove as much heat as you can from that material. So you're less and less efficient as you increase machine size. Now, this is one thing we look at when we talk about the pilot scale machine. This is important on a lab line. When you're doing lab trials on a small machine, whether it's a 26 or 32, and you do all your trials and development work on that size machine, and then you start moving in onto your production machines. Because of that factor, the loss in conductive heat transfer on that bigger machine, is you want to try to run that small line in an adiabatic type condition, which means we want to eliminate as much thermal transfer in and out of the material. And the idea here is to try to minimize the influence of electrical heating on that small machine and force that small machine to utilize its mechanical work, the screw. And so that way you're simulating your production scale up. Because again, on that production machine, depending on how big relative to your lab line, it's not near as efficient on conductive heating through your barrel heaters. And so the idea here is to try to minimize, electrical heating on your cooling system. So, for example, when you start the line, when you're running on a small lab machine, you can adjust the temperatures and try to, compensate for this. So, for example, if your barrel zones are actively heating, that means the material temperature is below the set points. So you want to gradually decrease the temperature of those barrels. You're trying to set the barrel temperature set points as close to the material temperature as possible. Same thing if the barrel zones are actively cooling, that means your material temperature is above their set point. So you want to gradually increase. So the idea here is to, while you're operating, adjust those temperatures so you get that set point as closely as you can to the actual material temperature. So the goal here is to minimize heat transfer and force that machine to primarily use mechanical work from the screw package. Now when we look at basic volumetric scale up and scale down, this is the exponent of 3 calculation. You can see here your target machine rate will equal your reference machine rate, and then you'll take the diameter of the machines in their ratio. You'll have the target machine diameter on top, reference machine on bottom, and you'll to the power of 3. So in this case, for example, if you achieved 550 pounds per hour on a 45 and you're scaling to a 70, you're just going to take that reference rate of 550, do the math, 70 divided by 45, and cube that, and you get 2070 pounds per hour. You can do the same thing on scale down. If you're going from, a larger machine, moving it to a smaller machine, the same thing. If you get on a 58, you hit 1,500 pounds an hour and you're moving to a 32, you would just take 32 divided by 58, cube that, and you get 252. So what this will do, the whole idea here is the fact that if this cubed exponent of 3 term, it tells us if I can put X amount in this machine size, I should be able to put Y amount in this machine size. And so this is just a basic volumetric scale up calculations when you move from machine to machine. So the power to volume ratio of the machines also needs to be taken into consideration here. And this is your specific torque divided by your center line distance cubed. So, most OEMs provide different torque density is another term we call it. A lot of times they'll have a lineup that could be a low power to volume, intermediate, and high torque is another way to say it. So, usually less than 10 is your lower torque rating machines, 10 to 15 approximately is your, intermediate, and usually above 15 is your high torque. And so here we'll kind of look at this and see if there's differences when I move these machines. You'll see what happens here if I'm going off of a volumetric scale up. So here's an example where you have a 32 millimeter pilot machine. That's a high torque density machine at 17.2. And you're going to move to a low power to volume 70. So your 70 is like less than 10, 9.6. Now you can see on the 32, you achieved 140 kilograms an hour. So if I do my math and scale that, 70 divided by 32 cubed times that 140 kg per hour rate, that tells me I should be able to put 1,465 kilograms an hour through that 70. But because it has a low torque rating, low power to volume ratio, it's going to have to utilize as much power on that machine that's available. So it forces you to operate at the maximum screw speed. And this is operating in both machines at 80% torque rating. And so, in the case of the 32, you're operating at 525 RPM, but when you move to that 70, and you scale volumetrically and you're on a low power availability, you're having to really push that machine to its maximum RPM. So if you're dealing with any shear sensitive, thermally sensitive type additives, you could degrade those materials. Now here we're going to look at the reverse situation of this, where we have a low torque pilot machine and a high torque production machine. Again, we're going to scale this volumetrically. So we achieved 125 on the pilot. We do the math, you end up with a scaled rate of 1308. And because you have a very high power to volume ratio, it's gonna operate at a much lower RPM level. And so in this case, on the pilot machine, you operated at 691 RPM. Let's say you got good properties, but when you go to the 70, you realize, maybe your dispersion quality is not as good because you're operating at a lower RPM. Now you could ramp the RPMs on that machine, but this is just to show you where these will operate differently at the 80% torque rating when there's differences in these power to volume. Now here is a situation where you're going to actually scale on similar torque densities, and this is ideal. It makes your life a little easier. Both of these machines are right around the 11 torque density. So as you can see, if you look at your scaled rate from 700 on the 58 machine, you get 1230 on the 70, and they're operating at 80% torque, relatively, pretty close, same RPM levels. Not far off. You're at 512, 499. So the idea here is to understand that when you scale these machines, if the torque density is very close, then you'll operate very close in the same RPM levels. But if the torque densities are quite different, you just realize your operating RPMs may be significantly different. So now we'll look at understanding shear rate and degree of fill. This is another factor to take into consideration, because when we talk about degree of fill, it's important to understand this, because we'll talk a little bit about effective shear. So shear rate is just your pi times your diameter, RPM divided by 60 over your clearance. Now you'll see here that the shear has a kind of a range of operating here. You have what's called your minimum shear is your channel shear, which is your deepest part of that screw channel, which is your greatest distance between the screw, the turning screw, and the stationary barrel wall, where your flight tip shear is your peak shear. And that one's important because this is where most of the energy input is imparted into the material. And you can see here for this example at a 300 RPM operating condition, the shear rate's quite different. You know, in the channel shear, you're at 85 reciprocal seconds, where you're at nearly 2200 on the tip. So here we'll talk about effective shear based on degree of fill. So a low degree of fill in the screw channel occurs at a low feed rate and higher screw RPM. And so this condition is an increased shear input because the reason is the material when you're operating in that machine, let's say you have a specified RPM you're operating at, let's say 600 RPM, and you start dialing your feed rate back, you start lowering it, that material tends to migrate up into the upper region of that tip of or the leading side of that screw flight into that higher shear region. On the high degree of fill is the opposite. Let's say you're operating again at 600 RPM, but you start ramping your feed rate. You start filling that machine more. As you do that, that material extends more into the lower part of that screw channel. And so this is a lower or reduced shear input. And you can see here, kind of providing a visual what that looks like. You get a very thin layer on a low degree of fill with most of the material in the upper part of that screw channel close to that maximum shear peak. But here on the high degree of fill, you get a larger volume fraction in that screw channel, and it starts migrating into that lower shear region. And so here, kind of again, another visual and explanation on this. If I try to calculate this and I look at this, the interesting thing is the actual calculated shear rate is the same. Because remember, shear rate's calculated on diameter, pi, operating RPM. But yeah, your clearances, the mechanical clearances are the same on the machine. But when we look at effective shear, this takes into consideration the material position within the clearance distance on what part of the shear region the material exists. So here, if you look at this on the arrows here, I'm trying to kind of find what's in the middle here. What's the average effective shear rate? And so, for example, on the left, I've got a lower degree of fill condition. I'm approximately 5.2 millimeters clearance there within that material volume fraction. So I'm getting about 423 reciprocal seconds. On the right side, I'm in a higher filled condition. You can see I'm 800 kilograms an hour at the same RPM. Now my material extends more into that lower shear region. So on average, that material clearance is about 10.3. So I'm 213 reciprocal seconds. So this is just to understand that degree of fill is important to understand as well here, that effective shear is what is the material experiencing depending on its position within the range or gradient of minimum and maximum shear region. And so this changes depending on your feed rate and screw speed ratios. And this is also what we call specific throughput. It's a very good measure on ramping a line rate up. And so specific throughput is your extrusion rate divided by RPM. If I can keep that ratio the same, I'm keeping my degree of fill very similar in that machine. So for example, let's say you start an extruder at 200 kilograms an hour and 250 RPM and you get good properties, but you want to ramp your capacity up, your rate, then you would try to keep that same ratio, which in this case, 200 divided by 250 is 0.8. So you have a 0.8 extrusion rate to RPM ratio. So then what I would do is, if I'm going to start pushing that line up, I want to keep that same ratio, 250. If I move to 250 kilograms an hour, then I need to bump my screw to 312 RPM to maintain that 0.8. If I move up to 300, I want to turn the screw to 375 and so forth. If I move to 350, I want to turn it 438. So that's keeping that balance of fill the same. And we'll look at another factor here. It's called diameter to clearance ratio. And this is important when we get into talking about wear conditions and design of the actual machine design. Some machines, as you increase machine sizes for different OEMs, whether I move from 26 millimeter, 32, 35, 40, 45, and so forth, the diameter to clearance ratio may not always be exactly perfect. And so one thing that's important here to understand is the shear rate will be equal for both machines at the same screw speed if the diameter to clearance ratio is the same for both machines. And so for this first example, and all this is your bore diameter divided by your clearance ratio. And that's where it lands in the shear rate calculation. You can see here, I've highlighted it down below in red. Is your pi times d times your screw speed is n divided by 60, and then clearance. And so in this example, when I take a look at this 26 millimeter machine and I do the math, you can see here how to calculate clearance. It's just bore ID minus your screw OD divided by 2. I've got a 0.1 millimeter clearance. On the 58, I've got a 0.25 millimeter. So those are relatively close. If you calculate and do the math, the diameter to clearance ratio, they're slightly different, but you can see here on the shear rate, they're going to turn, and one's at 48.25 reciprocal seconds for the smaller machine, and then the other's 43.92. But here's an example of situation where I have a 26 millimeter machine, as we previously calculated, has a 0.1 millimeter clearance, and a 70. When I look at the 70, it's quite different. It's got a 0.5 millimeter clearance. So when I look at that diameter to clearance ratio, it's somewhat different. So you can see here in this case, I'm getting quite a different shear rate on that 70 millimeter. And so where the small machine is at 48.25 reciprocal seconds, the 70 is operating 26.77. So in this case, when you move from machines, you may be able to operate that 70 millimeter at a higher screw speed to input similar as specific energy input. So this is just to understand there can be some design differences. So, these are things to take a look at before you go from machine A to machine B. Maybe evaluate this and say, is there a big difference? Now, this is hard to do when you consider the wear conditions. And that's what we'll look at next. Is you'll see the difference in of what it can make when you look at peak shear rates here. When we talk about a brand new machine with tight clearances, your peak shear rate on that 58's, 43.92 reciprocal seconds, whereas with just 2 millimeters of wear, it drops to 879. So this is, again, just, you want to be mindful of what is that. If you do monitor or measure your barrel ID occasionally, I don't know if that's something many of you do. It's more common for people to measure the wear condition of their elements, not as frequent or common to measure the barrel wear conditions. But if you have that data, you can kind of assess, generally speaking, your production machine, particularly when you're moving from a lab pilot scale machine to a production machine, more often than not, your production machine typically has increased wear simply because it operates, consistently all the time in most cases, where your lab line, depending on the level of use and how often you do product development or trials internal, it's usually not a continuous operating machine. So it's very common that it's has lower wear conditions. But again, all this hinges on what is the age of the machine. How often do you change these barrels elements? How often do you take measurements to assess the wear? But just be mindful of how this peak shear rate changes and can be quite different depending on wear conditions. So that's just another factor to look into. Now, when we talk about scaling up, most of the scale up on the volumetric that I've shown you so far has been based on the same geometry machine. And when I say the same DO/DI ratio, and so, a lot of what you see in across the industry, depending on the OEMs, 155 geometry is pretty common. But, there are other OEMs out there that offer different DO/DI ratios. So if you are moving from a machine, let's say you have a 155 45 millimeter machine, you have a 60 millimeter 166, how would you scale these? And this is where I move from the cubed term or exponent 3 term to what I call specific volume. And so you can calculate the specific volume of your machine. And in this case, this calculation here takes the OD minus the ID squared, and then times your OD again is divided by 1,000, because that's just converting to centimeters here, because you're noticing I'm using millimeter terms in the calculation, but it's cubic centimeter per diameter. And so that 1,000 factor is just a conversion factor to move from millimeter to centimeter. But you can see here it's 50.1 on the 45, it's 129.5 on the 60. And I would do a similar type calculation. It's just we're not taking the ratio of the diameter machines and cubing that. Here you're just going to take specific volume. So in this case, on the 45, you achieve 250 kilograms an hour. You take the ratio difference of the specific volume of the machine. So in the case of the 60, it's a 129.5 divided by 50.1. And that should tell you volumetrically scaling, okay, if I scale from a 155 machine to a 166, this is an approach I can take on what that rate should be on that 166 geometry. So here we're going to look at some examples of pre-evaluation of machine comparisons, just as some examples. So here again, similar to what we saw earlier in the webinar, I've got a 58 millimeter machine with 155 geometry, and I'm on a high torque density machine here. And I'm going to move this application to a 70 millimeter, same geometry, but it's a lower torque density. So again, what happens here, it requires that 70 now to operate at the upper RPM level. In fact, if I do a volumetric scale up, you can see here on the 58, I achieved 1,400 kilograms an hour. If I do the scale up, that tells me I should be able to push that 70 volumetrically, 2460. However, I have less power to volume, so I'm going to have to utilize as much of the available power on that machine as possible. In fact, it forces me to operate this machine at 90% torque at the maximum RPM, which is not ideal. Some people will operate like that. It just depends on how that machine's set up and the controls or the warning signals on torque levels. But this is just to show you can kind of pre-evaluate where will my machine operate. If I know my SEI, I know what available kilowatts I need. You can do the homework ahead of time. So you can look at what you've achieved on this 58, and before you even start pushing material into that 70 millimeter machine, you can do the math and say, okay, I'm operating at 0.109 specific energy. I'm running 1,400 kilograms an hour. If I scale this to 2460 and I multiply it times 0.109, I know how much kilowatts I need. So if I look at this and say, okay, I only have 298 kilowatts maximum on this machine, I need to operate at 268. Where am I going to operate on torque level? I'm going to be at 90% torque level. So what you can do here, in this case, is say, okay, I need to adjust the rate to target 80%. Let's say, okay, I really can't push this machine at 90% torque. So what I do and how to achieve this? Well, you can do the math here. And like I said, this is a little math heavy, but when you look at torque per shaft rating, first of all, you got to look at your design torque. What is my maximum design torque of that machine? It's 2208 Newton meters per shaft in the upper left here. And so I can take 80% of that value here and say, okay, well, if I'm going to operate at 80% torque, I need to be operating at 1766 Newton meter per shaft. And then I can plug that value back in, rearrange the equation to calculate kilowatts and say, okay, what's my available kilowatts at that 80% torque? And you can see here, you have 238 available kilowatts. Now I can take my specific energy and determine what rate I can achieve. And so you can kind of do all this math and say, okay, if I'm going to operate this machine at 8% torque based on this specific energy input, I need to be operating at 2183 kilograms per hour. And so here we are looking at this machine and say, okay, now we've got suggested operating conditions. I couldn't adjust my RPM because I'm operating at the max RPM. So now I'm moving this application from a 58 to the 70. I've had to adjust my scaled rate based on operating at 80% torque. So I'm now going to put 2183 kilograms per hour through this machine, operated at 625 RPM. Now you can look at another factor, a degree of fill. Remember, we talked about degree of fill. How filled is that machine under these conditions compared to my 58? Because again, that determines where that material position is in that shear region. So if I do the math on specific volume, now there's another calculation here for you called percent fill. This is an estimate of degree of fill or percent fill. And so you can see here in this calculation, it's your rate in kilograms per hour times a constant, 0.2777, divided by a specific volume times your operating RPM divided by 60. And then times specific gravity. And usually I take specific gravity as 1. Now, if you know your actual specific gravity, that's great. As long as if it's the same material application and you pick one, you can assume the same gravity in this, given that it's the same material application. And 0.35 is just what's called a conveyance efficiency estimate. That's a good general rule of thumb. It changes though depending on your screw configuration, but remember, if you match screw configuration from one machine to the other, you can make the assumption that that conveyance efficiency is going to be very similar. So there are some constants here to take, but when you look at this and I do the math and I say, okay, if I'm going to operate the 70 at 2183 feed rate, 625 RPM, I'm a little more filled on that machine. And so what that tells you, if have a slightly higher filled condition, that means I should have a little lower energy input into that. And when I look at this, I actually ran a simulation with these conditions at those rates. So you can see I ran 1,400 kilograms per hour at 800 RPM. On the 58, I ran 2183 at 625 on the 70. And you can see here, I'm a little less filled on the 58, so I should have a little higher energy input. And you can see I do get a little bit higher SEI. I'm a little lower on the 70 at 0.106 with a little lower melt temperature because of that higher filled condition. So if you want to take this a step further and say, okay, now I want to match the percent fill. And so what's going to happen here is, remember, we're operating at the maximum RPM level of 625. And so I can't, I could, to lower the degree of fill, I could ramp the screw speed, but I'm tapped out on the screw, so I've got to lower my rate. So if you want to go back through your percent fill and calculate what that rate is, you could, I adjusted that calculation. You can see percent fill calculation up top is your rate times 0.2777 divided by specific volume times your operating RPM divided by 60 times gravity times efficiency. But if I rearrange that equation and solve for my rate, you can see here, I want to put that 70 at 0.78. In the calculation, it's decimal form. And so 0.78 and proceed with the calculation. Now I need to drop the rate. That tells me I need to reduce that rate from 2183 to 1925 to get the same degree of fill as I had on that 58. Again, like we said previously, when you increase fill, that material grows into that lower shear region. And vice versa, if you want to decrease the fill level, it's going to migrate back up in that higher shear region. So now I'm trying to match this and say, okay, these should operate very close on energy input. Now I did a simulation again. However, there wasn't a change on the specific energy. The temperature did increase from 197 to 198. So it didn't work out perfect, but that's kind of the gist here is, I know that it seems like a lot of steps and a lot of work, but this is just some guidelines to kind of help you, take a look at the differences in these machines. And when I scale volumetrically, where does that put me operating in the power? If I want to push that machine at 80% torque, what's my available kilowatts? Where am I going to have to operate on my RPMs? Is it going to be similar to the other machine? What's my degree of fill? I can take a look at that. And so in a perfect world here on machine transfer, you would want both machines to have the same L/D, so you can match conveying and mixing length. You would scale on exponent 3 to have similar volumetric fill. Torque density, very similar. It'd operate in similar screw speed relative to feed rate. Same element geometry, conveying and KB, pitch, length, stagger angle, which would give you similar residence time and residence time distribution. Same DO/DI ratio, same bore diameter to clearance ratio. And both machines are in similar wear condition states. So this would be, in a perfect world, to make life easier to be able to scale these. So the summary here is there was a lot of information, a lot of math thrown at you, but ultimately your ultimate goal here is to match specific energy input on both machines. Your properties should be very, very similar. The key thing to begin with is try and match those screw configurations as closely as possible with similar element type, pitch, stagger, length, diameter ratio. Adjust solids conveyance to focus on matching melting and mixing section of the process for differences in overall L/D. So if you're going from short machine to long machine or vice versa, try to adjust the solids conveying. Basic volumetric scale up is a good place to start to develop similar volumetric fill. Use specific volume scale up, scale down for different DO/DI machines. So this is again moving from 155 to 166 or vice versa, or to 1.8 or whatever the difference in those DO/DI ratios is, to use specific volume. Look at your power to volume differences to determine if available power is suitable for the scaled extrusion rate. It'll tell you where it's going to operate in the RPMs. Keep in mind differences in design, diameter to clearance ratio, or wear conditions. And again, keep in mind when scaling from smaller lab pilot scale machine to higher, the higher efficiency and heat transfer compared to the larger machine. Again, as you grow that machine size, you become less and less efficient on thermal transfer through the barrel heating. So hopefully this was a little helpful. A lot of the slides were quite busy, a lot of math in there, but the whole idea was to give you some guidance and just some things to consider and look at, and you can kind of sit down and do your homework ahead of time before you just go out there and start pushing material through the machine and turning knobs to try to make it work. You can actually do some pre-assessment here and say, okay, what are some differences? What are similarities? What are some things we can look at ahead of time to give us a really good starting point on feed rate relative to RPM? Should we see similar degree of fill? Assume similar shear input, and then once you get ramped up running, you can tweak as you need to match your specific energy. So now I'll turn this over to Christian.
Thank you, Daron. We have a few questions for you. What determines torque density? Does a higher torque, or do higher torque machines, are they more reliable than lower torque machines?
Not particularly. Really, it's all about what the customer wants and needs. It's for production minded, and in most cases, most people want equipment utilization, so they want to maximize their capacity on the machine. The high torque densities, or we also generically translate them as high outputs. You have a lot more power available on that machine, so you can really push rates. For example, on a 70 millimeter machine, I've seen 900 horsepower motors and allow people to operate, 4,000 to 5,000 pounds per hour on some applications. So it's not really so much reliability. It's just, hey, how much power do you really want to get as maximum output?
Okay. And then how do you calculate the degree of fill?
Yeah, that percent fill, that's in that slide. I snuck it in there. That percent fill. Once you get a copy of the webinar, whichever one should, you'll see that percent fill. It's an estimate based on specific gravity, conveyance efficiency. It was that calculation I utilized in the webinar.
And then you had an equation in there. I'm not sure if you'll be able to recall this one, but there is a 9549. What is that in the equation? If that rings a bell.
Oh yeah, that's just a constant on kilowatt calculation. That's to calculate torque specific, your torque per shaft. 9549 times kilowatts over RPM. Yeah, that's just a factor to get to Newton meters.
Okay, perfect. Well, thank you very much, Daron, and everyone who joined us. A recording of this webinar will be available on 1cpm.com within the next week or two, where you can also find all of our previous editions as well. This concludes today's webinar. If you have any questions or would like more information on what CPM can do for you, please email us at extrusion.sales@cpm.net. Thank you.